In this video, we're going to talk about 9.7 Taylor polynomials and approximations. We'll also be talking about some power series here. So we're going to find polynomial approximations of elementary functions and compare them with the elementary functions. We're going to find Taylor and Maclaurin polynomial approximations of elementary functions, and we'll use the remainder of a Taylor polynomial. These notes are going to all be completed. So go ahead and follow along with me today. Polynomial approximations of elementary functions. We've done this with linear functions to find a linear approximation. For example, we created a linear approximation of f of x is equal to e to the x at x equals 0. We found f prime of x was equal to e to the x. At x equals 0, f prime of 0 is equal to e to the 0 is 1. So that would be the slope of the tangent line. And then we also evaluated the point here. F of 0 was 1. And so we wrote the slope-intercept form of the line here. Y equals mx plus b, so y equals x plus 1. And this is only a good approximation if we're really close to x equals 0. At other x values, even x equals 1, this approximation is not as good because this function is growing so quickly that even over here, x equals 1, we would have 1 plus 1 is 2, and e to the first is 2.71. something. So it's really already starting to be quite different, noticeably different there. So a polynomial expansion about a point. You can approximate a function f of x by a polynomial p of x when you choose a value x equals c such that f of c is equal to p of c, and require that the slopes of p of x and f of x at c match. F prime of c needs to be equal to p prime at c. So that ensures that p of x resembles f of x at x equals c. And the polynomial function will be a good approximation of the function near that point x equals c. If we get too far away from that point, then it will no longer be a good approximation. So show that f of x equals e to the x and p of x equals 1 plus x plus 1/2 x squared have the same first and second derivative at x equals 0. So e to the x, when we differentiate it, it will be e to the x. When we differentiate it again, it will be e to the x. So when we take the derivative of p here, we'll get 1 plus 1/2 times 2x is 1 plus x. We stick in 0 here for e to the x, we get a slope of 1. When we stick 0 in here for f prime, we get 1 plus 0 is 1. That's good. F double prime e to the x, f double prime of 0 is 1. If we take the derivative of 1 plus x, we get 1. So f double prime of 0 is also 1. So there's y equals e to the x, and there's p of x is this pink function. Look how good of an approximation that is for e to the x really close to 0. They overlap for quite a bit, or almost overlap. Much better than this purple line here, y equals x plus 1, that is only good for just a little bit, and then the blue function pulls away so quickly. But the pink function is also increasing right along there with e to the x. So at least to the right over here, it seems like it's a pretty good approximation. Over here to the left, the pink function is actually above the blue function, but still staying kind of close. So a few more polynomial approximations of y equals e to the x. So p1 of x is 1 plus x. We just talked about p2x, the second degree polynomial that approximates e to the x, is 1 plus x plus 1/2 x squared. P3 is going to be 1 plus x plus 1/2 x squared plus 1/6 x to the third. And I don't know if you're going to see the pattern here. If not, we'll show you here with when we get to P5. So we're going to get 1 plus x plus 1/2 x squared plus 1/6 x cubed plus 1 over 24 x to the fourth. And if you haven't noticed the pattern yet, the division here is 1 factorial, 2 factorial, 3 factorial, 4 factorial. That 6 times 4 was 24, so 5 factorial. Here, 5 times 24 is going to be 120. And so e to the x is exactly the sum from n equals 1 to infinity of 1 x to the, actually 0 there, x to the n over n factorial, like that. That's what it is. So this is x to the 0 over 0 factorial is 1, x to the 1 over 1 factorial is x to the 2 over 2 factorial is 2, x to the 3 over 3 factorial is x to the 3 over 6, and so on. We just add all those up, x to the 5th over 5 factorial. The next one, P6, would be 1 plus x plus 1/2 x squared plus 1/6 x to the third plus 1/24 x to the fourth plus 1/120th x to the fifth plus 1 over 720 x to the sixth, and so on and so forth. So this is just one of the types of polynomials that we're going to talk about here, this expansion of e to the x. And the more terms that you go, the closer and closer and better your approximation is. But how good is good enough, basically, is the question. So what's our margin of error that we are allowing ourselves? So the definition of the nth Taylor polynomial and the nth Maclaurin polynomial. Maclaurin polynomials are just special types of Taylor polynomials that are centered at x equals 0. So that's what we want to know is if f of x has n derivatives at x equals c, then the polynomial p sub n of x, the nth degree Taylor polynomial here, equals f of c plus f prime of c over 1 factorial times x minus c plus f double prime of c over 2 factorial times x minus c of 2 squared plus, and then keep going, times plus the nth derivative of f at c over n factorial times x minus c to the n. So we can actually just say p sub n of x is the summation from n equals 0 to infinity of this term fn at c times x minus c to the n. I need to scooch that over just a bit. Like that, or you can write the x minus c to the n separate, like that. If c equals 0, then we have a Maclaurin polynomial. Maclaurin series. I'll call this series. I'm going to call this a Taylor series. Here, where we have p sub n, or we can call this f of x here. We call this f of x here is equal to, and then all of these things stays the same thing. You just evaluate them at 0. So this is, let's say f of x here. F of x equals summation from n equals 0 to infinity of f n at 0 times x to the n over n factorial. The reason it's just x to the n there because x minus nothing is x minus 0 is x, and then it's x to the n. So that makes it a lot easier for us. We like Maclaurin series when we can get them. Simply because evaluating at 0 usually makes our life easier. Usually. Find the equation for the nth Maclaurin polynomial, or the Maclaurin series, for f of x equals e to the x. So all the derivatives up to f of n is e to the x. And all of them, when I evaluate at 0 here, f of 0 is 1, f prime of 0 is 1, f double prime of 0 is 1, f triple prime of 0 is 1, dot, 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 fn of 0 is 1, always, all the time. So this is going to be 1 plus 1x plus 1 over 2 factorial is 1/2 x squared plus dot, 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 plus 1 over n factorial x to the n. So this is going to be this f n of c part is a 1 here, x to the n over n factorial. N goes from, this actually is going to have to go from 0 to infinity. 0 to infinity, or to n, x, and they just replace with a k so I can get the n there, but that needs to start at 0, not 1. Okay. Find the Taylor polynomials P0, P1, P2, P3, and P4 for f of x equals ln of x. ln of x is a little strange because we actually can't center it at 0. We're going to have to center it at x equals 1 because 0 is not in the domain of ln. So remember, you have to put something in for your c that's actually in the domain of your original f of x. It has to be centered at a point that's actually on the graph, not on an asymptote. So if we take, the reason we want 1 is because ln of 1 is 0, and that's very nice. And then we have 1 over 1 is 1. And then we have 1 over negative 1 over x squared, that's a negative 1. And then we end up with a positive 2. And then we end up with a negative 6. And I think you can start to see that we have the factorials here, but they're alternating in sign. So that's 0 factorial, 1 factorial, 2 factorial, 3 factorial, and so on. But we have this 0 term. So we really just need to kind of start with n equals 1 and kind of forget about the rest here. So P0 is going to be f of c is going to be 0, and then p of 1 is going to be f of c plus f prime of c times x minus c is going to be 1 times x minus 1 is going to be x minus 1. and then 0 plus x minus 1 minus 1/2 of x minus 1 squared, and so on and so forth. And we're going to get 0 plus 1 times x minus 1 minus 1/2 of x minus 1 squared plus 2 over 3 factorial is going to be 1/3 of x minus 1 cubed, and so on until we get to out here. If this is 0 plus 1, x minus 1 to the first minus 1/2 of x minus 1 to the second plus 2 over 3 factorial of x minus 1 to the third plus, and then it's going to be -6 over 4 factorial of x minus 1 to the fourth. Now this thing here is always going to be related to this factorial that was down here, so we're only going to be left with the previous, or with the index down there. So if I keep going here, this should always be over n, so it's going to be x minus 1 to the 1 over 1 minus x minus 1 to the second over 2 plus x minus 1 to the 3 over 3, and so on to -1 to the n plus 1, I think it is, because this is 1 and that's positive, so it's off by 1 there. X minus 1 to the n over n. That's what that turns out to be for Pn. So ln of x equals is exactly equal to the summation from n equals 1 to infinity of -1 to the n plus 1, x minus 1 to the n over n is what it appears the pattern is up here. Now find a third order Maclaurin polynomial. This one, 0 is in the domain of sign, so we're going to want to use x equals 0 if we're allowed to, and compare the values of f of 0.1 and p3 of 0.1. So derivative of sine is cosine, derivative of cosine is negative sine, derivative of negative sine is negative cosine. We want to go out to the third derivative here because we're going to a degree 3 polynomial. So f of 0 is sine of 0 is 0, f prime of 0 is cosine of 0 is 1, f double prime of 0 is negative sine of 0 is 0, and f triple prime of 0 is negative cosine of 0 is -1. So there's my coefficients there, that this is going to be f of 0 plus f prime of 0 over 1 factorial times x plus f double prime of 0 over 2 factorial times x squared, and so on. So I'm going to go out to 3 here. This is going to be 0 plus 1 over 1 factorial x plus 0 over 2 factorial x squared plus a -1 over 3 factorial x cubed. Sine is an odd function, so I'm only going to see the odd powers of the polynomial here, never any even powers. 0 and 2 were all zeros. That's what it means to be an odd function, is that these polynomials will have, these polynomial approximations will all be odd terms like that. So we're going to have x minus 1/6 here. 3 factorial is 6, x cubed, and then we're going to have plus some epsilon, a little bit of air here because this is an approximation. So next time we'll talk about how to find this this margin of error, this epsilon. So how does P0 compare with F0? If we put zero in here, it's 0 minus 0 is 0, and sine of 0 is 0, and they're exactly the same, which is what's supposed to happen. If this is centered at 0, f of 0 should be the same. So we're going to go just a tiny little bit away from 0, like 1/10, and we're going to see how close they are to each other. So for small values of sine of x, it should be about, but not exactly, this value. It's really, really, really close. Look how close this is to 1/10. It's only off by 0.00016 repeating. So the but look at how close P3 is here to sine. They agree all the way out here to the 1, 2, 3, 4, 5, 6th decimal point, and it's only in the 7th decimal point right here. So that is the millionths. I think it's 10 millionths. Tenths, hundredths, thousandths, 10,000ths, 100,000ths, millions, 10 millions is where they start to disagree. We're usually not going all the way out to the 10 millions. So if we were rounding anywhere here within the first 5 or 6 decimal points, we'd be golden. So that this polynomial would do a great job at approximating sine to that level of precision. So how does P3 of 5 and f of 5 compare? Not going to be so good because 5 is so far away from 0, right? So it's a much worse approximation to x equals 5 because notice that if we found the difference here, let's see, this is how we actually find the error, is we take the difference between the two and we find the absolute value. So our error right now is only 0.00000000833267. That's what I was saying, that they agree to the, I think we said 10 millionths spot, but that's what our error is. But if you would actually figure this out for 5 and find out what sine of 5 is, 5 radians that is, and put 5 into that polynomial, I'll let you do that as an exercise for yourself. You'll figure out that it's much worse error here. All right, so f of x is the exact value of f at x, and then that should be exactly equal to p of n if I account for all the terms, the polynomial of degree n approximation, plus there's going to be some remainder or some error, epsilon is what we called it just a second ago, some margin of error. And knowing the accuracy of an approximation technique is important. So to find the error, which we were calling epsilon just a second ago, we can find the remainder from this Taylor series, which is going to be the absolute value of f of x minus p sub n of x. That's what we just did up here. So find the difference between them and take the absolute value. So Taylor's theorem, theorem 9.19, if a function f is differentiable through order n plus 1 in an interval I containing x equals c, then for each x in I, there exists a z between x and c such that f of x equals f of c plus f prime of c times x minus c, and you already know all that there, that's the Taylor polynomial there of degree n, plus the remainder here, where r of n is equal to the next derivative here at z over n plus 1 times x minus c, the n plus 1. This is called the Lagrange form of the remainder here. Don't worry about all that. That's just the names for them. But you're basically looking for the next term here in the polynomial, plus or minus. That would be your possible error in this approximation. So for example, if we have P3 of 0.1 minus sine of 0.1, we already found this here. The old technique here where we took f of x minus P3 of x like that, found the difference between them. But now instead we want to find the remainder using this form here where we say that we want to find the n plus 1, so the fourth derivative at some value z over 4 factorial times x minus 1 to the fourth. So let's go ahead and see what that would be. Recall that the third derivative of sine was equal to negative cosine, so the fourth derivative is going to be sine again. So R3 of x is going to be sine of some z value over 4 factorial times x to the fourth, and x is going to be 0.1 is what we're sticking in there. So the x value where you're approximating f of x using P3 of x. So that's going to be sine of z times 0.1 to the fourth over 4 factorial. That needs to be less than or equal to just this 0.1 to the fourth over 4 factorial. Forget about the sine z part, since I am saying that that has to be between -1 and 1. So the biggest that this value can get is an absolute value of 1, and that's going to be 0.1 to the fourth over 4 factorial comes out to be 0.000004, and that 0.12345 to 3456, and this is definitely within that margin of error that's allowed there. So this is exact, this is approximate right here. Determine the degree of the Taylor polynomial Pn of x, expanded about the point x equals c equals 1. That should be used to approximate ln of 1.2 so that the error is less than 1,000th. All right, so first, how many terms do we need to go out to ensure that is basically our question. So we use the remainder and say that we want this remainder to be less than 1,000th. So and we were doing sine of x up there. So here's our pattern here, and we're only going out to 5 here. Why are we going out to 5? Because if we solve this here and we get fn plus 1 of z is -1 to the n plus 1 minus 1, which is part of the formula here, n plus 1 minus 1, again, part of the formula because it's centered at 1. factorial over z to the n plus 1. That's going to be -1 to the n times n factorial over z to the n plus 1. And when we take the absolute value here, the -1 to the n is going to go away. And we're going to be left with n factorial over n plus 1 factorial. So that's going to give us n plus 1 in the denominator. We're going to have 1.2 minus 1 is going to be 0.2 to the n plus 1. And we're going to have z to the n plus 1. And then that r of 1.2, we need to have less than 1,000th. So we're going to have 1 over z to the n plus 1 times n plus 1. 0.2 to the n plus 1 needs to be less than 1,000th. So if we look at this, this part here is the biggest that it can get is 1. Z is going to be some positive number here. So we're going to put on the right-hand side over here that this is less than 0.2 to the n plus 1 over n plus 1 needs to be less than 0.001. And then we're going to take the reciprocal here and switch the direction of the inequality. And we get 1,000 here. Then we're going to stick in here 1/5 in the place of 0.2. And we're going to find that this is 1 over 5 to the n plus 1 in the denominator. That's going to be a reciprocal that comes to the top. So this is n plus 1. 5 to the n plus 1 is greater than 1,000. Peel the 5 off so we can get the 5 to the n there. And divide by the 5 is going to be 200, and 5 to the n times n plus 1 is going to be greater than 200. So there's 200. There's 5 to the n times n plus 1. We're going to have to graph it and see where that's at. So n has to be 2.51159. So we need bigger than that. So n equals 3 is the degree of the polynomial that's needed. So we come back here and we know these degrees of these are these nth derivatives up to 5, but we really only need up to 3 here to satisfy the conditions for the remainder. So let's go ahead and write that out. Is going to be x minus 1 to the first minus 1/2 of x minus 1 to the second plus 1/3 of x minus 1 to the third. If I stick 1.2 in there, then I can approximate right there. Now let's find ln of 1.2 with our calculator, and let's look at the actual margin of error here and the difference here, and take the absolute value is going to be 0.0003451 is going to be less than 1,000th. It's 3/10 of 1,000th. It's 3 10,000ths. So what if we wanted an approximation accurate to tens, hundreds, thousands, 10,000ths, millions, 10 millions? We would need a lot more terms is what we would see. So you can do that on your own and figure out exactly how many terms you would need to make this here be not 1,000, but 10 million. And you're going to need to go out to a lot more terms for that. All right, 9.7, exercise number 51 from the edition of the textbook here, I think was the 10th edition when we were making this. So if you want f of x is equal to sine of x and use that to approximate f of 3/10 to a degree of accuracy less than 1,000th using the Maclaurin polynomial, then we're going to need to figure out what degree we need to go to, or we can just figure out a whole bunch of derivatives here until we can figure out the pattern is what we're up to here. And then we can just write the generic Maclaurin polynomial for it here and see that all of the even powers are going to drop off, and I'm only going to be left with the odd powers of x minus c. Actually, that's just going to be x to the n that I'm going to be left with, because we said that c is going to be 0 here. We're doing Maclaurin, so I'm not going to have to worry about the minus c part. So we're going to see that this turns into, it's going 1, -1, 1, -1. So this is -1 to the n plus 1 here. And then that's over n plus 1, because this power and this factorial need to match each other. And this is going to be x minus c, so 0.3 minus c is 0 to the n plus 1. I'm only dealing with the odd powers here. So then this is going to be forced to be less than 1,000th. And when we solve this out, 0.3 to the n plus 1 over n plus 1 factorial is less than 1,000th. So we can make that 3/10 to the n plus 1 for n factorial. It's 3 to the n plus 1 over 10 to the n plus 1 is 10 times 10 to the n, and this is 3 times 3 to the n. So we're going to take the reciprocal here and switch the direction of the sign and get 1,000 over there, multiply by this 3 and divide by this 10 to get 300. And then we have n plus 1 factorial times 10/3 to the n needs to be greater than 300. Look for the point of intersection in your calculator, and you get that 300 is somewhere between 2 and 3. You need to go out to degree 3, and you notice that a lot of times these Taylor polynomials, these Maclaurin polynomials, don't require you to go out to that many terms, which is exactly why your calculator uses them to calculate things like sine and cosine and tangent and log and natural log and all these other types of functions that you wonder how in the world does it calculate those things as a calculator that I thought it could only add, subtract, multiply, and divide and just do it really fast. Well, if it uses the Taylor expansion of these things and it goes out to just, not that many terms, it can get a really good level of precision. Now, 1,000th is not going to be good enough for us when the calculator goes out to 12 decimal points, but we get significantly better approximations as we go out to more decimal points or more terms. So we may only need to go out to 5 or 6 terms or so on. Even if we went out to 10 terms, the calculator can do that really easily and do it really quickly, but it doesn't need to do an infinite amount of terms to get within the level of precision of what you can see on the screen. All right, that's it for this video. We'll come back next time and we're going to have a big set of notes that's going to dive deeper into this, and with Taylor series, Maclaurin series, power series, interval of convergence, radius of convergence, and so on. So we're going to take what we learned about the ratio test and sometimes the root test, but usually the ratio test, and apply it to a series like this and try and find and what we call an interval of convergence for a power series, specifically one that approximates a rational function in the form of 1 over 1 minus x, or something close to that. All right, that's it for this video. We'll see you again next time.